Hey everyone, so today is Tuesday. I wanted to follow up on yesterday's lecture, which was the COVID-19 updates, and we did a little bit of algorithms review. And specifically, I wanted to put out this video basically redoing that second interview question. We had a few little hiccups during class during the live lecture. Basically, we ran out of time, and the original algorithm that I had in my head wasn't working. So I wanted to do an update and put up a video in case any of you were curious and you wanted to rewatch it. So let's get started. I'm going to share my screen here. So there we go. All right, cool. So again, the problem was if you have, for example, some array, let's say it's something like 6, 3, 4, 1. Then you want to count how many numbers to the right of a single number are smaller than it. So 6, all the numbers to the right of 6 are smaller than it. So this is going to be a 3. The 3, only the 1 is smaller than it. So that's going to be a 1. The 4, the 1 is smaller than it. So that's also going to be a 1. And the 1 has nothing to the right of it. So that's going to be a 0. So this is going to be our input. And this is going to be our output. So in order to do this, we have our brute force solution. So really quickly, our brute force algorithm that we were thinking about in class was basically a 2 pointers. So you have 2 pointers I that goes from 0 to n, where n is the size of input. And then you have j, which goes from I plus 1 to n, basically. So basically all you're doing is checking, is input j less than input I? If so, then basically do count plus plus. And then at the end of this inner for loop, you basically say out I equals count. And then once you've gotten all of those counts, you can just return out here. So that's going to be 2 pointers. We basically have, so let's talk about the complexity here. So first of all, the space complexity, we should be able to see theta of n, I believe. Basically, only our output array is our extra space. The time complexity, however, is going to be, we have 2 for loops. We have our I loop, which is theta of n, and then a nested j for loop, which is theta of n. So we multiply the 2 together, and that's going to be a theta of n squared total time. So can we do better? Let's try to do better. Can we do better? So like I said yesterday, we have a few different algorithms that we can use. So we know that when we're looking at how many numbers are less than or greater than a number, that automatically makes me think of a binary search tree. So let's take 6341 up here again. 6341. If we put these numbers into a binary search tree, then we can figure out in a BST where the numbers that are less than a certain number are going to live. So let's think about the properties of a BST. So a couple things. I'm actually going to make my pencil a little smaller. Cool. So the properties of a BST, we know that all left nodes smaller than current, then let's say the root. All left nodes are less than the root, and all right nodes are greater than the root. So that means that to find the nodes, find all nodes smaller than, to find to find all nodes smaller than node n, we want to do two things. So let's make this into a BST real quick. So we have a 6, then we add a 3, then we add a 4, and then we add a 1 here. So that's what our BST is going to look like. If we have a 3, the nodes that are bigger than the 3 are going to be two different things. So you want to look at all of n's right children. And you want to look at if n.parent.val is greater than n.val, then you want to also say that everything in n, so you want to say, this is going to say n.parent is greater than n.parent is greater than n, obviously. And then all of n.parent.right are also greater than n. So this is going to be super important. So we have two different properties that we have here. Now, the problem here is going to be that if we construct a BST going left to right here, if we start at 6 and then we add in 3, 4, and 1, now suddenly if we look at all the values smaller than 3 after we construct this, then there's going to be issues because let's say we do this in pieces. So I'm going to go back here and erase that BST, and we're going to do it piecewise. So we add a 6, and we look at everything in the BST that's bigger than, that's smaller than the 6. There's nothing in it. So we're going to end up having a 0 there. The 3, once we add the 3, we're going to say what's smaller than 3? Again, 0. Then what about the 4? We add our 4 in. What's smaller? We say that, oh, sorry, these should not be right. So I'm going to change all of these. So we're going to go back here and say all of n's left children. And then we're going to say down here, these should be left as well. Cool. So if we put a 4 here, then we say the parent is less than n.val. So then all of n.parent.left are also less than n. So here we're going to have a 1. And then we add a 1 here. And then again, the parent is greater than, so the parent is actually greater this time. So we're going to have a 0. So this isn't what we want. We don't want 0, 0, 1, 0. But basically, what if we start from the end and then insert the other way? So let's try doing that. So again, I'm going to erase our BST if my pencil will cooperate. Okay. So let's start from going this way. So let's say we insert a 1. Now there's nothing to the right of it. So our output array is going to look something like we add a 0 at the end. Now we add a 4 in. So let's add our 4. Then we say the parent is less than n.val. So we want to count the parent. So that's 1. And then all of the parents left. And that's null. So that's just going to be 1. The 3, we add a 3 here. And then the 3, the parent is smaller. Okay, so the parent is actually bigger here. So we want to keep recursing up. I think that's what we want to do. We want to keep going up until the parent doesn't exist anymore. So let's go all the way up to the 1. So we look at the 4, then we look at the 1, and we say, aha, the 1 is actually smaller. So 1 and all of its left children are smaller. So then we count that as 1 as well. And then we have a 6. So we're going to add a 6 into here. Oh, sorry, not there. We're going to add a 6 here. And then that 6 now, we're going to do the same thing. We basically say for 6, all of its parents, basically. So we look at the parent, it's smaller. So we add it and all of its children. So the 4 and the 3. We look at the 1, we add the 1 and all of its children. So we add all of these as well. So now we're going to see a 3, a 1, a 1, and a 0. So that's going to give us the right output. Now, how do we actually convert this into pseudocode? Let's try doing that really quickly. So let's figure out what we did. Oops, I just made a bunch of extra pages. So we had our 6, 3, 4, 1, just like before. What we want to do is traverse input array from right to left. Add a new node to an AVL tree with value, let's say with index I, for example, with value input I, basically here. So right now we're going to start by inserting a new node with value 1. Then we're going to keep doing that, but along the way, we're going to calculate num smaller nodes. I'll define what that is later. And then we can basically say output I equals calculate num smaller nodes. And let's say this is, let's just say this is I here or something like that. Or let's say this is current node. And then we also need to pass in the root. Okay. And then what we're going to do is if I equals -1, return out. And that should be our total thing. So let's figure out what calculate num smaller nodes does. So calculate num smaller nodes. So basically this is going to be called after we insert a new node, basically. So what we're going to do is take in our node wherever we are, and then say, let's go and calculate the size of left subtree. So that should be pretty straightforward. In some way, we could potentially just do any sort of traversal. So one option, do some traversal and calculate how many nodes. So that should be pretty straightforward. So we should be able to do that. So let's calculate the size of the left subtree. And we want to say while parent exists. Actually, before we do that, let's define a new variable. So we can say, let's say that the input is current node. And then we can say right now, parent equals current node dot parent. And then we can say while the parent exists, what do we want to do? We want to say if the parent value is less than current node dot value, then we want to add size of subtree, add size of parent's left subtree to count. And that reminds me, we want to initialize count here. So let's say count equals 0. So then here with calculate size of the left subtree, let's just say that we want to add that value to count. So we want to do count plus equals this. And then here we basically are going to do the same thing. So this is going to look something like count plus equals size of parent's left subtree. And then basically we're going to keep doing this while the parent exists. And then the only other thing we have to do here is parent, current equals parent. Yeah, current equals parent. And then we can basically say, oh, let me cross this out and write this a little cleaner. We can basically say, here, let's do something like this. While parent equals cur node dot pair exists, we do this basically. And then we can basically say cur node equals pair. Again, all of this is pseudocode, so we have to actually convert this to code, but I will leave that as an exercise to you. So all of this is within the while loop, so I'll end the while loop here. This is just while backwards. This just indicates that the while loop is done. And then after we're done with all of this, we just say that we are going to return the count. So that's our algorithm, basically. We're going to calculate the num smaller nodes, and then the output I is going to be whatever the value for calculate num smaller nodes is, and then we're going to decrement I, basically. So all of this is going to go inside of a for loop. So let's rewrite this line of code with this traverse. So this can basically be something like for I equals input dot size to 0, we do this whole thing. Sorry, to -1. And then we can do all of this. And then actually we want this line of code here to be the first thing that we do. So this is our base case basically. If I equals -1, return out. And then we can name all of this as one function where we just say, this is going to return an array of integers. So it's going to, so it's going to be an integer array, and it's going to say get smaller vowels to right, and then it's going to take in an integer array here as the input. So that's our algorithm here. And again, I'm going to leave this as an exercise for you to convert it yourself from pseudocode into actual code. But that should be it. If you have any more questions regarding this algorithm, just shoot me a message on Slack, shoot it in the general solution, shoot it into the general chat, or you can post your answers in COTD-solutions, and other people can give you a code review. I could give you a code review, whatever helps the most for you. Cool. That's it for everything. I hope you enjoy your day, and I will see all of you tomorrow in lecture, hopefully. Bye.